So, welcome everyone to Guided Study Group Week 12 of Math 140. So, hopefully, everyone has done great on the midterm too, and we're now ready for the materials for final exam. Yay! So, we're gonna get started. So, this week we're just gonna mostly focus on antiderivative and also kind of like how to actually put it into definite integral. And so first we have section 3.9, which is antiderivative. So the definition of antiderivative says if f is called an antiderivative of another function, small f, on an interval, if you have the derivative of big F is the first derivative of the big F is small f for all x in that interval. And then you have the theorem. So if f is an antiderivative of that on a function, then the most general antiderivative of small f on I is fx plus c. So for sure, in the fact that you have, so say if you have fx plus 1 or fx, both of them when you take derivative is going to be just f of x. So when you take derivative, so it doesn't really matter what constant that go along with big F. So you can have 1, 2, or like even 1,000. You're gonna still get that derivative. So the most general form is plus the c, which c is a constant. And to find the c, usually you're gonna be given maybe like an extra conditions in the problem statement. Say you have is going to have maybe like the first condition, like f of something, f of a is equal to b or something, and then that b is gonna let you, when you plug in x equal a into fx plus c, when you plug in a in here, you're gonna be able to find what it's c with respect to b, and we're gonna see that in the example. Don't worry. Table of anti-differential formulas. And so to do this, you have these are kind of like, so the concept of antiderivative is very broad, and every single time you take antiderivative, these are kind of like a general formula for the most common functions. So first one, when you have a function c multiplies small f, then the particular antiderivative we're gonna c multiply big F. Of course, they're gonna be always a plus c in all of these things. So following that, I would say in this entire table, this one is the most helpful because you're going to see this right now a lot, and even in Math 141, which the entire material for first midterm is on integration and antiderivative and all of that. So that's some of the common functions and how to find the antiderivative given the formula. We also have antiderivative for trigonometry functions, say cosine, sine, tangent, and secant. Then, of course, you also have for cotangent and cosecant, but this is not like very necessary here, and of course we're going to touch more on that in 141, so no worries. So that's all I have for 3.9. Let's get to, oh, not just that. We have, this part is kind of like the additional one. When I saw at the end of your lecture slide, Dr. Kasha kind of mentioned the concept of indefinite integral. So indefinite integral is abbreviated, is denoted as with an s and then fx dx. So this is kind of like a Greek way of writing s. And that's kind of like the sum, which we're going to touch on more in 4.1, like the next sections. This is the notation of indefinite integral. It's also the notation of a general antiderivative of fx. So just the thing of notations, which in 141 you'll be directly use this notation without really kind of introduce it much, and even in the next section 4.1 and 4.2. So I just want to introduce you guys to these things, kind of like familiarize yourself a little bit. Then you have some of the representative problems. So some of the things that you might be asked, okay, for this sections is say they're gonna ask you to find the antiderivative given the the function itself and one special point of the antiderivative. Second one is draw the graph of big F from the graph of small f. So this is kind of like similar to what we learned in midterm 2, where you try to graph f from f prime. It's kind of like, I think, section 3.5. Even though we didn't actually graph it, it's more like we're given a graph of f prime, we're trying to find something about f. So this is kind of the same thing. The only difference is that to put on a higher level where we try to find where we try to even graph it out, so the relationships between f and f prime in every single point on a domain. And then the last one is more like an applications of it related to kinematics. So the relationship between velocity, acceleration, and position is that acceleration is the derivative of velocity, and velocity is the derivative of function, of the position function. So if you to do so, this is kind of like a perfect relationship so that we can apply antiderivative. So you're gonna maybe given the velocity acceleration function and value of 1 point, so you can find the actual velocity of actual function of velocity or acceleration, and then you'll be given an initial value of position and velocity. So first, say you're given acceleration and v of some point of a of b, then you'll be able to find what is v of t. And then you also be given a initial value of, say, velocity or position s of c. Then you have what is s of t, the general antiderivative. And we're going to see that, I think, in the second example. But that's kind of like most of the questions that you can be asked in these sections. It's not hard. It's kind of like just a new concept, and most of you might not have touch on it in your high school calculus, so it can take a while to understand this. So the first example is question 41 of section 3.9. So phi small f, or phi like the antiderivative, given that you have the second derivative be the cubic root of t, minus cosine t. So this is what we have. F double prime of t is cubic root of t minus cosine t. Now I can rewrite this one as t to the 1/3 minus cosine t. This one is easier for me to use this formula. So just 1 plus c. Antiderivative is going to be x to the n, and then antiderivative of cosine t is negative sine t. So what we have is f prime of t. So from here to here, you take antiderivative once. So you have n is 1/3, so you have x to the 4/3 over 4/3 my plus sine t plus c1. So it's going to be 3 over 4 x to the 4/3 plus sine t plus c1. So this is one term of the antiderivative. However, we need to find what is the complete antiderivative. So what is f? So what we do is we want to take antiderivative again. So you have ft. So you have 3/4 is the constant. We keep it based on that table. Whatever constant that we have in front of our function to take antiderivative of, we keep that constant. So now n is equal to 4/3. So you're gonna have x 7/3 divided by 7/3. So that's that. Then antiderivative of sine is negative cosine Oh, this one is, I kind of messed up. This is a negative. This is a negative. This is a positive. Because derivative of cosine t, no, derivative of sine t is going to give you cosine t. So kind of like antiderivative of cosine t is sine t. And then antiderivative of sine t is negative cosine t. Make sure that you kind of get this part because it's like confusing. There's a very clear distinction between what antiderivative that you're trying to find. If you're trying to find antiderivative of cosine, is sine. If you're trying to find antiderivative of negative sine, is cosine. Remember, this is a negative here. So then you have plus c1, not, yeah, sorry, I kind of put everything in x, which is not supposed to be the case, but okay, t, and then plus c1 t plus c2. Or you can kind of simplify this 9 over 28 t 7/3 plus cosine t plus c1 t plus c2. So now here you see that you have two constants and you don't have any value of. That's when you start to use this condition. So that's when I say when you're asked to find the antiderivative of something, then you usually going to be given the function and like kind of like the derivative of that thing, and then you're going to need some initial points of the function to find all of the constant. So say you have f of 0 is 2 is equal to this is 0 plus cosine of 0 is 1 plus 0 plus c2. So c2 is 1. Then you have f of 1 is also 2. This one is equal to 9 over 28 plus cosine of 1 plus c1 plus 1. So this one is going to give us c1 equal to 13 over no, it's going to give us 1 minus 9 over 28, which is going to be 19 over 28 minus cosine 1. So now you found both of the constant. So your final answer is that ft is equal to 9 over 28 t to the 7/3 plus cosine t plus 19 over 28 minus cosine 1 multiply t plus 1. So calculations wise, I might make some mistake, but the general method is that you have to find antiderivative until you get the function that you want. Of course, you're going to have some constant in there, which is c1 and c2 here. That's when you start to use the conditions given in the problem statement. So that's example 1. Now we go on to example 2. A stone is dropped from the upper observation deck of a CN tower, 450 meters above the ground. Find the distance function of a stone, find the time it takes to reach the ground, and the velocity at the contact moment. Now when you look at this is the point that it gets dropped down. So initially, v0 is 0 because you drop it down, you're not throwing it down, so there's no initial velocity, right? And so I'll make the reference scheme where you're going downward is a negative direction, and when you go upward is a positive direction. Now from that we only know this height compared to the ground is 450 meter, and there's nothing else that we can actually use to derive the function. So look at this. If you want to find a distance function, you need the velocity function, and so you need the acceleration. Let's see what do we have here. We have the first one point of the velocity, and we have the acceleration. This is subtly indicated, but always when you drop something from above the ground, it's going to be subject to gravitational acceleration. Then so you have a here is going to be negative g. G is always going downward and have the value of 9.8 meter per second square. So therefore we have, for the first questions, you have A with respect to T is negative 9.8 meter per second square. And this one is negative G. Then you have so you have V at 0 is 0, and then S of 0 is 450 meters above the ground. Then, so you have first antiderivative. You're going to give us V of t. So velocity is antiderivative of acceleration. You're going to have negative 9.8 t plus c1 meter per second. Then you have, using the first conditions given, V0 at 0. V at 0 is 0. So when you plug in t equals 0, you're going to have negative 9.8 multiplied 0 plus c1. So you have c1 is 0. Then you have conclusion of the function of vt is negative 9.8 t meter per second. Now when you take the distance function, is from here to here, it's another antiderivative. So you have this gonna equal negative 9.8 t squared over 2 plus c2. Or you can simplify this at negative 4.9 t squared plus c2. And then using the first condition as well, you have s at 0 is 450. This one is equal to 0 plus c2. So you have c2 is 450. Or you have s of t is negative 4.9 t squared plus 450 meter. Now you have the distance function to find the time it takes to reach the ground. So at first you have s equal 450, and when you reach the ground you have s gonna equal 0. So you have s at t equal to 0. So basically you just try to find t that give you s of t equal to 0. So you have t is going to equal square root of 450 over 4.9. Then this one is going to be, I think I have numbers. That one is going to be 9.58 seconds. So this is the time it takes to reach the ground. And then you need to find the velocity at the contact moment. So now you have t, you just plug it in the function of v. So you have v of 9.58 seconds is going to be, plug in, you have negative 9.8 multiply 9.58, which is going to be negative 93.91 meter per second. Now, this is why is the velocity negative? It's just the fact that you can, here you can kind of grasp it by the way velocity is negative, but it's negative 93.91. It means that the speed of the objects when it reaches the ground right here is 93.91. Speed is always positive, so it's just a magnitude of the velocity, but the direction is that it's going downward, so it's a negative. That's all we have for the first part of example 2. Now, example 3, if the stone is thrown downward with the initial speed of 5 meters per second, how long does it take to reach the ground? And now this one is where you have the first condition of velocity change is at t equals 0, v at t equals 0 is negative 5 meters per second. Negative is again because it's thrown downward. The direction is negative. Therefore, we have v of this one, v of 0 is negative 5, is also equal to negative 9.8 multiplied 0 plus c1. So now your c1 is going to be negative 5. And so your vt is negative 9.8 t plus 5 meter per second. Actually negative 5. Then when you take antiderivative, to find the position function, you're going to have s of t is, let me do this one quickly, negative 5t plus c2, or you have negative 4.9 t squared minus 5t plus c2 meter. Now, first condition is still s of 0 is 450. Therefore, you have again the same thing when you plug in, and then you're going to have s equal negative 4.9 t squared minus 5t plus 450 meter. Now, you want to find the time width of contact again. So you're going to solve for t where you have s of t equal to 0 again. So this one is negative 4.9 t squared. Negative 5t plus 450. If you solve for this t, either using trial and errors, plugging in number, because like the previous questions kind of like give you an idea of, okay, what range of t the issue false form. So if you just plug in, or you can use like other algebraic, say like delta in the way to solve quadratic function, that's completely fine. But if you actually come to solve this, you're gonna have two answers, t equal negative 9.086 second or t equal negative 10.1 second. Now, time cannot be negative, so you ignore the solution. So this is your answer of the time it takes to reach the ground. So as you can see, we just use antiderivative maybe one or twice using whatever conditions given. And just based on that, just repeat the steps so it's not too hard at all. You just need some time to kind of like familiarize yourself with the concept of antiderivative. Okay, so now we go to 4.1 and 4.2. It's where we actually use come to the definition of things like Riemann sum or distance and area under the curve. So the definition, we have the area A of the region S that lies under the graph of some curve of some continuous function is the limit of the sum of the areas of approximating rectangles. And so this is very clearly seen in if you have the graph. I think you're really familiar with this one now because this is what we use in the lecture notes. So when you divided it by infinitely many rectangle and sum them all together, they have the same length of base with just different height depending on the value of x that you're looking at. When you divide them into infinitely many small rectangle like this and sum them together, and as you take more and more rectangle, the total sum is just getting closer and closer to the actual curve under the area. And so you set the limit of that with n approaching infinity. The same thing with the distance travel. So say if you have this graph is the velocity. So this is velocity. Then everything under the curve, and then this is time. So everything under the curve of this, when you try to take many of them, it's going to be the distance travel. So again, you're gonna divide them into smaller and smaller rectangle so that you sum them together. Then what you're gonna have is that you're gonna have the distance travel or just the area under that curve of the velocity. That's 4.1. Nothing really special. And then you have 4.2. This is where you come to the concept of definite integral. So we have the definition. So definite integral of a function f from a to b is denoted in the form of s fx dx from a to b. And that one is going to equal to the limit of n approaching infinity of the sum of the many rectangles that we have in 4.1. Provided that this limit exists and give the same value for all possible choice of sample points. If it exists, we say f is integrable on this interval. So then we have the theorem. If f is continuous on that interval a to b, or has only finite number of jump discontinuity. So this is the important part of jump discontinuity and finite number of that. So say you don't need to have a very nicely continuous function, but say you only have finite number of jump discontinuity. So the type of discontinuities that this thing is available is very specific. It has to be jumps. It cannot be the infinity one or maybe the removable one. Then f is integrable on that interval, and this one exists. So basically it's saying if you have a continuous function or a relatively continuous function on an interval, then f is integrable on that interval. And then if you have that, this integral is gonna equal to this limit of the sum of the area under the curve. So it's gonna equal to the area under this curve of fx from a to b, and that's gonna equal to the area of all of the small rectangles that we have. And where you have, if you have an interval, say from a to b, the base of each rectangle is going to be this length, which is b minus a divided by n, and xi. So every single xi that you take for fxi is going to be this a plus I delta x. So a plus whatever length of the function, because whatever length of the rectangle. So say if you have 3 rectangle in between these points, then you're gonna have a plus 3 delta x. So it's kind of giving us what is value over here. Now, there are some properties of definite integral that we should know. So about the boundary of an integral can be switched with a negative in front of that. And then if you have a equal to b, then you kind of like, you have an integral from a to a of fx dx, and of course this one is going to equal 0, because if you want to find an area of a point on a function, it's going to be of a function regardless of the graph, it's going to be just 0. And then integral of a constant is that definite integral of a constant c dx is c multiplied b minus a. So c c would be, because this one, when you take antiderivative of that is cx, then you plug in b and a, you have c b minus ca, which is c b minus a. I think that one we're gonna touch more clearly on section 4.3 and 4.4 next week, but this is kind of like the logic behind it. Then you have this property of plus and minus, like a sum and a difference of the integral of a sum and a difference is equal to the sum and the difference of 2 integrals. And if you have a constant, the integral of a constant multiply a function is going to be that constant multiply the integral of the function. And then we have this, you can split the interval of taking integration from a to b to a to c plus from c to b. That's the property of definite integral. And then finally, we have comparison properties. This is kind of like the extra. I don't think Dr. Cash will actually go over this, but we can talk about this a little bit, kind of like not amazing, kind of surprise yourself too much if it appears in the quiz or something. So if you have f of x is always positive on an interval, then the integral is also positive. Clearly, you can see the fact that if you have a positive function, the sum of all of these positive is always going to be positive. Then if you have fx is bigger than gx, so you have fx, then you have gx. So say on this interval from a to b, then you have this area under fx is bigger than the area under gx. This is another clear thing. And then finally, if you have This is M, and this is big M. So if you have this, say this function, so clearly, then you have this is A, B, and this thing is B minus A. So you have this area of F under the curve is bigger than M, this small rectangle, and is smaller than the area of the big rectangle when you have this one. Right, the area, the integral, which is the area under that curve on that interval, is going to be squeezed between the area of these two rectangles. And so that's all the theory. So now we're going to go to example. So example 3 is question 30 of section 4.2. Express the integral at the limit of Riemann sum. Do not evaluate this limit. So from this one, you have the area is from, the interval is from 2 to 5. So A equal to 2, B equal to 5. So you're going to have delta x is 3 over n, with n approaching infinity. With xi is going to be 2 plus I 3 over n. So this one, we're going to have equal limit n approaching infinity. You have 2 plus 3i over n squared plus 1 over 2 plus 3i over n with dx. So you have dx is 3 over n. Now, let's simplify our expression. You can choose to simplify it or not, it's up to you. I would say in these scenarios, I wouldn't simplify it because it's going to make my entire thing very complicated. So just the thing to note here is that whenever you ask to express an integral, the two things that you need to specify is xi, what is the general formula for xi, and what is for delta x. And so after that, you just need to plug in. Delta x is going to be the one for dx, and xi is just going to be plugged in here. So that's example 3. Then you have example 4 is the reverse way. So say you're given the Riemann sum and find what is the definite integral. And so a very clear pattern appears in this problem is this part in the bracket. So it's kind of like giving me a general idea of A plus I delta X. I think I'm missing an I here. Yes, I'm missing an I. Then you're gonna have this one is equal to xi. Then I have A is equal to 2 and delta x equal to 4 over n. This one is b minus a over n, which is b minus 2 over n. So b is 6. Therefore, you have, if you put this one into the form of what we're supposed to look at, like the general form of the Riemann sum, you have 1 minus xi squared, 4 plus xi squared, delta x. Therefore, you have this one is the integral going from 2 to 6. Fx is going to be this one. So you have 1 minus x squared, 4 plus x squared dx. So this is a definite integral that we have to find. So again, just know the concept of what is xi and delta x, and especially in this question, being able to see the pattern. I'm sorry for missing an I there, but I'm going to add it in. Yeah. But that is what it's supposed to look like. So this is the final answer for this example. Again, you should be able to do it both way, either going from an integral to the limit to the Riemann sum and the reverse way. So kind of like being able to do both way because you don't know what you're going to be asked in the quiz or the exam. And this is kind of like just the fundamental understanding of the problem. So now we have the last question. Example 5 is question 38 of that section. Evaluate the integral by interpreting in the terms of areas. So you have, this is the sum, no, this is a difference, so I'm going to put it in the form of a difference. So you have x dx minus from -5 to 5 square root of 25 minus x squared dx. Now, if you look at the end part of the lectures where you asked to find this integral, so you're going to graph each of them individually out. So you have first is x, y equal to x, from -5 to 5. Clearly, you can see the fact that these two parts are exactly equal in magnitude to one another. They just have different size. So I would say, because this is an odd interval, no, this is an odd function for x, y equal x. So the area, the integral, taking on a symmetric interval against the about the origin, this one is going to be 0 because they're absolutely equal in magnitude, just different in the size. And then this function. So this function is square root of 25 minus x squared. So it's like half of an angle with the radius of 5. So this is giving me the area of under the half of the angle of the circle. So you're gonna have this one equal to half of the area of a circle, which is half of pi 5 squared. So this one is giving me -25 over 2 pi. Note the fact that now you have to look at, is it above or so at -5 is 0. But then when it's 0, it's going to be positive. So it's going up this way. It is not the other way because this one is going to give you a negative area. So, but this is not the way because you have to look at the way that it goes. So it's go from here to here, right? So that is, be very careful with the directions of where you go. So from here to here, it is 5 because both of them are equal. But this one doesn't cancel anything out. Everything is either all positive or either all negative. So you have to be careful of the direction. Is it positive or is it negative? Now, having said that, that's all I have for today. If you don't have any more questions, please feel free to try all of the suggested problems, and I'll be more than happy to help you guys during the weekend. Having said that, I'll end the meeting here, and I'll see you guys next week. Thank you for coming.